Welcome to NOAA Central Library's educational platform for the presentation of research and ideas in support of the National Oceanic and Atmospheric Administration's mission. Today's library seminar is titled SSMSE, a tool for management strategy evaluation using stock synthesis operating models. The presentation is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries and organized by Kristen Blackheart. Today's speakers, Dr. Nathan Vaughan and Kathryn Doering, will be introduced by Kristen. But before I hand over the mic, here are a few housekeeping items for our live audience members to improve your viewing experience. If you have trouble with the audio or visual components of GoToWebinar, we suggest that you log out and rejoin us. This resets the software and usually resolves most technical issues. Our presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I've added the link to our channel to the chat box. We're very interested in your questions and we encourage you to ask them throughout the seminar, even though the speakers will not address them until the end of their presentation. All audience members are muted, so type your questions or comments in the chat box under Questions, located in the control panel of GoToWebinar. So with that last detail, let's get started. The mic's yours, Kristen.
Thanks, Lisa. Today is one of those cross-regional, cross-platform projects that we love to see. So I'm really excited to learn more about the SSMSE tool and excited to introduce Kathryn and Nathan, who are some of our really skilled developers that we have working with the agency. Excuse me. Nathan is a research scientist that works with the Southeast Center. His research focuses on improving fisheries management through development of more accurate forecasting approaches and associated software tools. And he's been doing some really impressive work with forecasting approaches at the Southeast Center. And then Kathryn works at the Northwest Center and is involved heavily in maintenance and development of the stock synthesis software platform, which is a generalized modeling framework for stock assessment and associated R packages for SS. Her interests include developing software tools to improve the process of conducting stock assessments. So with that, I'll hand it over to Nathan, and thank you both for being here.
Thank you so much, Kristen and Lisa, for the introduction. And thank you for inviting us, and thank you everyone for coming and spending the time to listen to us today. We're going to talk to you about SSMSE, a tool that Kathryn and I have been developing for the last 2 years in order to perform management strategy evaluation using stock synthesis assessments directly as operating models. I'd like to start out by thanking all of our collaborators at the Southeast, as Kristen pointed out, at the Southeast Center and at the Northwest Center. It's a very big group of people who came up with this original idea and have been working on development with us, and also other collaborators at other science centers and in academia that have been working on testing out this tool and being our very helpful beta testers along the way. Also, we'd like to point out the other R packages that we use directly within SSMSE. Like all of this is open source and it's built upon a lot of work that people have done previously. I would like to particularly point out R4SS and SS3Sim that are foundational to being able to perform all of these analyses. We've worked closely with Ian and Kelly and incorporating them into SSMSE and also adding back in some features to their packages from work we've done here. And also our funding, that was an internal NOAA MSA grant that was awarded to John Walter in 2019 and 2020. So that was what helped us do all of this work. So just to start out, a little bit of background. I'm sure a lot of you are familiar with this, but management strategy evaluation is primarily a strategic planning tool for helping guide our efforts in stock assessment and data collection. So in simple terms, it uses simulation to test the performance of different alternative management procedures against a suite of pre-specified objectives and over a range of specified uncertainties. While MSE in general could often be very complex, using models like Atlantis ecosystem models. This SSMSE is specifically a single species MSE simulation. So it's not overly complex, but it's just the right amount of complexity, we think, for a lot of situations. And in general, MSE is, as this figure on the left shows, the simulation process where you have an operating model, which is your perceived true real world scenario. You've got some function that will sample data from that operating model, be that catch or indices of abundance or size or H comps. So it's sampling data out of that, and that will be fed into this management strategy. And that's a sort of a broad term that encompasses everything from that raw data coming in to final catch allocations coming out. So that might be a complex stock synthesis assessment model that's happening in every iteration, or it could be a simple data limited index that's just adjusting catch based on a single index of abundance or size composition. So, but that's the general framework for what's happening in MSE. As is apparent from the name and the title of this presentation, we're building on stock synthesis, which is a generalized platform for stock assessment. It's very widely used, particularly within the US, and it's been applied to over 220 US federal stock assessments to date in the last decade. So it's providing a really wide breadth of existing resources that we could potentially use for MSE if we could get them implemented within a management strategy evaluation. It's also been used not just for stock assessments, it's also been used for research, and as of relatively recently, it's now available not just on the VLab, but it's also the source code is available up on GitHub, so you can dig into that to your heart's content. And we also have the reference here for Mather and Wetzel. Stock synthesis, it has not just been used for assessment, as we noticed, it's also been used already for MSE in a number of cases, particularly in the Northwest. However, these were all single-use cases. So it was a custom MSE that was designed with custom goals and for a specific assessment. And usually with one or two core analysts developing this code in the timeline of like a stock assessment question. So a relatively short time frame to turn around results on these things. SSMSE wanted to build on the success that these previous attempts have made at developing MSEs directly using stock synthesis. And so we have this goal of creating a generalized and standardized tool that could directly use any existing SS assessment or any given SS3 stock assessment as an operating model for future MSEs. And we wanted to bundle that into an R package, which is now available up on GitHub as a beta. Still, in testing, but it's fully featured now. And you can simply install that using the remotes function package in R and referencing, you can see down the bottom, the NIMS Fish Tools SSMSE source. And that will install it directly into your R library. The reason we wanted to go towards a generalized tool is that there are potentially a large number of problems that arise when we rely heavily on these single use case and single developer projects. As always, it's very time consuming to write code. Anyone who is also programming and stock assessment scientists will know that there's a lot of work involved, and it's difficult when you come back to potentially reuse that or adjust that later on. As you can see in our little dummy example down below, you've often got a lot of fixed things in there, hard-coded paths on the analyst machine, hard-coded values for things that you're interested in, such as, in this case, natural mortality at a range of different values. A lot of things that just you may, especially as you get into a detailed design, you end up getting stuck with these little hard-coded values hidden in your code, and it's not always apparent where you need to change things, how you need to change things, and it makes it very difficult to extrapolate that to a generalized case. Particularly in the timeframes of assessments and single research projects, you're going to have a lot less eyes on the code. You're working over a shorter time frame, and you're only working within probably a small research group. So maybe a few other people that are going to get to see what's going on behind the scenes and give you feedback and bug testing of your code. and that's going to mean that it may not be reproducible on other people's machines, especially if your code is not widely available. And it's then on the back of that particular analyst to make sure they share this out with other users who may want to build upon it or adapt that code. So it's just a lot more restrictive and potentially error-prone. So we came in to say, could we build this generalized solution, particularly for MSE, given those previously stated issues of the time-consuming nature of developing software. If we could generalize these results so they'd be applicable to lots of use cases, then it makes it far more reasonable, in this case, to have spent 2 years developing a piece of software, if not only us, but a large swath of users can run MSEs using that and save themselves considerable amounts of time in implementation. Again, by getting that out there to multiple users and multiple stock assessments and multiple questions that they're asking, we're going to get a lot more eyes on the same code and a lot more chances to bug test and identify those issues. And we've already found that we've been collaborating with people at the Southwest Center, and they're finding bugs and issues along the way and helping us improve our code. So getting out there to multiple different users and getting lots of different backgrounds looking at your code helps you find all of those bugs that you may not ever see in a single use case piece of code. And that's going to help our reproducibility for future analyses. If you do an MSE in a generalized tool, then publish that, someone can go back, read what you did, and rerun that same code themselves and replicate your results and make sure that they understand what's going on and that people aren't making errors unintentionally. And we're able to do that because it's this simple MSE structure. We're focusing on this operating model standpoint, allowing that to be SS, but it's a very simple framework to have that OM sampling, simple sampling structure, and then a management strategy. And Kathryn will talk more later on about implementing custom management strategies within SSMSE. So why would we want to use the stock synthesis models? As I said before, there's been a lot of use of SS. There's over 200 existing assessment models. Building OMs is really a lot of the time the hardest part of doing an MSE analysis, apart from the computational time, is building that robust and rigorous operating model. So stock assessments have already gone through that. They've gone through an extensive peer review period process in order to develop that assessment. Due to the importance of getting accurate stock assessment results, is getting a lot of eyes on the particular stock assessment. So we're leveraging a huge amount of effort and man hours and research time that have gone into developing all of these assessments and then trying to leverage them for new research questions. SS, as a generalized and widely used tool, provides a good standpoint with a rich set of options and nuanced details, as you can see on the right, for Big Eye Scape. You have a large amount of flexibility to add complexity, and this is just time-varying natural mortality, but you have a lot of nuance there to create complexity, which is often even more detailed potentially than what is needed in a stock assessment. So even if you've already intending to use an SS model as your EM, you could potentially add a lot of uncertainty and variability in that model through SS's different time-varying options and area-specific structures than you would have in your assessment model. So you can test a lot of detailed features. What can we answer? This is really the purpose of doing this. What are we trying to do with MSE? A lot of things we want to look at, potentially what sort of management strategies work best. So different harvest control rules, or what will work best under different potential impacts of climate change. We could look at what model is going to work well if growth is shifting or natural mortality is shifting with climate change. How could sampling, different sampling strategies impact your stock assessment accuracy? So could we reduce sampling in one area, or should we shift sampling from one data source to another? And we can test how big of an impact that's going to have on different assessment results. And also things such as stock assessment complexity. We can look at, do you need an extremely complex stock synthesis assessment model, or could you get away with a more simple EM or assessment of management strategy, a harvest control rule, or a surplus production model, or something simpler that we could implement? So you can test things like that. Looking at the general workflow of SSMSE, it really breaks down into two key functions. We've got the run SSMSE function, which is where you describe, you've got your inputs and existing assessment models for your OM and potentially your EM. That's your main run SSMSE function that's going to output you a bunch of info from your runs and also new model files from all of those operating model iterations. And then we have the SSMSE summary function, summary all, and that's really where we take all of those thousands of iterations and scenario runs and work to summarize all of them into useful data that we can gain some insights out of. So means and standard deviations of key parameters such as spawning stock biomass and landings and variability in landings. And then we output these all as data frames and CSV summary files. And at the moment, we're relying on the user to define what plots specifically they would like rather than build in a suite of simplified options that may not be applicable to people. We're focused at the moment on giving them just the raw data outputs summarized and allowing them to make their own key plots. If you'd like more information, we'll give you some in this talk, but there's also links here to the README and the user manual that are both available up on GitHub and give a lot of detail on. The README has a full walkthrough of an example application, and the manual goes into more detail about all the specific features and functions within SSMSE. So within, like I said before, within the MSE process, we have this run SSMSE function you see up on the left. It will take your operating model, so you give it a stock assessment, a stock synthesis assessment, the final fit assessment. It'll take that and then it will create it into an OM. It just turns on some of the projection capabilities. It turns off some variable features that cause issues, but it basically restructures that and makes sure all your files are set up correctly to run that as your operating model and sample from. It then will sample future data or historic data from that OM and feed that out with associated uncertainties and potential biases. And then it will run it'll feed that into your management strategy, and that may be, like I said, a complex SS assessment. It could just be a data control, harvest control rule, but it'll feed that in, and from that management strategy, you're going to create, depending on how many years you have between assessments in your projection, your simulation, then it's going to project that many years of catches, which you feed back into your operating model, potentially again with implementation error, and then you'll apply that into the operating model to run, to sample another n years of data. So step the model forward. If it's 5 years, 5 more years, sample that data out, and then feed it back in your management strategy and repeat until the end of your simulation. And then you'll repeat that over and over for all of your different scenarios and different iterations within scenarios as you specify them in the code. This is your main input. I know it's a little intense, but this is your main run SSMSE function. So the non-highlighted things are fairly standard, defining your different scenarios, defining how many iterations you have per scenario, defining the file path locations of your operating and estimation model, defining how many years you want the simulation to be run for, and defining how many years are going to go in between each assessment, and then also a random seed, which lets you replicate your results. So if you put in a fixed seed, then all your randomization will be reproducible from run to run, so you can test bugs. We are going to focus on primarily, Kathryn will be talking about this MSVec input, which is the type of management strategy. She'll talk about how that can be the EM or custom OM, and then I'm going to focus on walking through the sample structure list, which is how we read data in order to output it from the OM to your estimation model, and future OM list, which is how you specify changes in your operating model into the future. So the SSMSE sample list, the sample structure list function, all of the sampling is currently implemented within SS, the SS Bootstrap capabilities. We worked with Rick to increase those capabilities to more data types. So now I think all the data types are available to be bootstrapped into the future. And we have, in order to get people up and running, a create sample structure function, which will read your DAT file from your OM and then create a template for sample structure. So if we go to the next slide, on the left here, you can see this is your this is the object, it's a list object. Each of these is a little input in that list of that data. So you've got catch, and you're specifying what years, seasons, and fleets, and the standard error of those catches that you're going to sample. In this case, it's every year for the 6 years of our projection. CPUE, in this case, it picked it out as once every 5 years. It's going to, if it can find consistent patterns in the historic data, it will replicate them here, but only relatively simple patterns. So here for length comp, you can see there is an NA. In year, it wasn't able to find any useful patterns, so it just gave you a dummy input. You're going to have to update that with a specific year, or you can replace the length comp with a null, and then that will remove it, and then as it won't throw an error. And similar with age comp, mean body weight, mean size at age. You've got a number of data types that you can sample from, and you can adjust that either the standard error for some of these or the sample size for the composition data. And that's how you would look at differing impacts of changing your budget for sampling, increasing or decreasing sample size to improve your estimates for those options. So we had originally thought that the data side, and often that's the approach, is to try to add more realism into your data sampling and uncertainty, try to make it better reflect your true variability in year to year in your data streams. We found that no matter how much you mess with the uncertainty in the data, it never really truly reflects that historic pattern. So we developed this future OM list capability to randomly adjust, or not, you can specify how it works, I'll go through it, to adjust parameter values in the OM into the future. So this is now actually able to modify any SS parameter value in a time varying fashion. It uses the deviations approach within SS, the parameter deviations, in order to create any possible pattern that you can define. And that allows us to introduce much more realistic process error effects on top of standard potential impacts, such as changing parameter mean in order to look at like potential climate change impacts. This allows you to look at that year-to-year variability and process error. So to specify this, like I said, it's a list object. So this is going to look at what we do in that case. So we've got a Parse input, so that allows you to specify which parameters this is going to apply to. In this case, it's just natural mortality, and you can provide any parameter name, like I said, that are available in the. You can read those names from the read SS Parse function in R4SS. It also lets you put in recdevs, which are your equipment deviations into the future, and implementation error as well. And you can also set an all, which will apply to almost every value. It leaves out a couple of the stop recruit curve parameters because they're conflated with recdevs. But that would let you just do something like random jitter on parameters into the future, as opposed to like specific trends that would probably never be applicable to every parameter. But it's there just in case people want it. You can then have the scenario input. Here is a vector. The first thing you put in is going to be either the word replicate or randomize. If you randomize, it means that all your scenarios and iterations are going to be purely random. So your random number in all of those different combinations are going to be unique. If you replicate, it's going to replicate the same random deviations in a given iteration across scenarios. So if you want to do a fast test of a particular analysis, you could replicate your deviations so you don't have that iteration to iteration uncertainty incorporated into the analyses. And then after that, you're going to put in either a value all, in this case, which means it applies to all scenarios, or you can name the specific scenarios, scenario 1, scenario 2, to just apply a change in that scenario. And then, you've either got model change, which is allowing you to define within SS how the parameter is going to change and let SS randomly sample its specific values into the future. And if you do that, you need to also specify after that the normal or log normal to define what sampling distribution will be used. If you don't fill that out, it's going to default to normal. And then there's also a custom option, which would allow you to put in fixed values in the future for that parameter. So that lets you do any kind of complex change you'd like in the future that could be specified by some external model or simulation plan that you have. So that gives you a lot of flexibility to do anything that you need. And then the data frame, this is where you input your values or your pattern that you want to use to modify these values. So you've got up there the years for averaging, first and last. That's defining a range of historic years that you would like to look at in order to calculate what your value should start off as. So your starting point for the new value there is going to be an average from years 1 to 100 of the model. As opposed to if you put it in as an NA, it's just going to use the value of the last year of the model. And then we have the last year original value and first year final value. That's the transition period. So if you put in, say, year 100 and year 101, that would mean that you had your historic value up to year 100 and straight away shifted to your new value in year 101. In this case, we've got 100 to 110. So it's going to do a linear interpolation of the change between those two values over those 10 years. So you can add simple linear trends in a parameter value over time. And then when you're specifying this, rather than specifying the raw value, you're actually specifying functions or functions of a model to parameterize random draws of these values. So you can specify the mean or the standard deviation, or also an autocorrelation factor that will go into an AR1 autoregressive function. Each of these can be adjusted, and then you're going to use one of three methods. It can either be additive, which means you're just adding to, in this case, the historic value that you averaged, or multiplying that value. And there's also a replacement option where you just specifically define the value. You don't multiply or add to the historic. You just so in this scenario, or with this average, you're adjusting the mean of the natural mortality value is going to increase by 0.2 over the first 10 years of the model. And then the standard deviation of the uncertainty around that mean is going to multiply by 2 over the next 10 years of the model. So I'll show you the next slide, but this is just the output of the actual list object this would create. So you've got a second way of looking at it and understanding what's going on. And you can see that this creates 2 objects, and you can add as many objects as you want to this list, and each one of them implements a specific change, and they can build upon each other. So you can have changes in mean and then changing standard deviation on top of that, and you can have a second shift running over the top of that, like a previous change, and you can apply it to different parameters as you go. So you can add as many changes as you like. That's up to you. So in this case, we did the time varying M, and as you can see over the years 100 to 110, that blue line, the mean, increased by 0.2, and then the gray confidence bands you can see then increased over the next 10 years. And what you would get in your operating model would be the M's represented by these yellow points in one particular iteration. This is just a random draw, but you would replicate multiple of these for each iteration, so you'd have different natural mortality. As an alternate example, so I have time varying autocorrelated selectivity. So for this example, I added some autocorrelation to this, and this would just be the size of 50% retention, say, for a fleet. And this isn't changing, the mean isn't changing over time, but you're able to add in this random drift through the autocorrelated variance. And if you look at the top and bottom range of that, the mean is 20, but it ranges from about 15 to 25. And so you could see similar thing here would show that it's a selectivity curve for that fleet and how it could adjust the parameter bounds that it would adjust vary within during time. And then that would result in this potentially differing outputs through time for your length compositions. So this would be if you, in a year when you're at the bottom of that range, L50% equals 15. Then you might have a year where you're back up in the mean and you see your size comp shifts a little to the right, and it could shift even more when you're at the top of that range. So this, the goal of this is that it could really much better reflect some of these shifts you see that just can't, no matter how hard we try, be explained by sample uncertainty, given a fixed selectivity curve in your estimation model. It's just, we see these shifts happen, but it's impossible to explain through pure data issues. So this is the approach we've taken for now, and we'll see how it pans out. But this should allow you to make very nuanced changes in your operating model. With that, I think I've gotten to the end of my section, and Kathryn's going to take over to talk to you about the options for management strategy.
Thanks, Nathan. And so this is the last option that we're going to be talking about today for the options available in the SSMSE tool. So this is the management strategy options, and there's 2 main groups here. So the first option is what we're calling an EM option. And so with the EM option, this uses a stock synthesis model as your estimation method within the management strategy. And then in order to get projected catch by fleet, it actually uses the forecasting module within the stock synthesis model itself. The other option is a custom option, or the ability to write your own R function. So basically how this works is this function will need to be able to read in a stock synthesis file that includes sample data from the operating model and output catch by fleet. Within those bounds, you should be able to write any sort of R code that you want to do in order to change your management strategies in the simulations. So now just to walk through in a little more detail with this EM management strategy, once again, it runs a stock synthesis model and uses the forecast settings to get projected catch by fleet. One helpful ability is that the code in SSMSE itself is able to change the number of years automatically, so you don't need to worry about those years. Just all of the other settings in the forecast are what you could set to get your projected catch by fleet. And in order to use this management strategy, we have a little code snippet down at the bottom here showing the run SSMSE function. And down at the bottom, this MS-vec input. So for this one, we're showing this vector is length 2 because it's indicating options for 2 different scenarios. So in both cases here, we're using the EM management strategy. So the other input that's needed is this EM directory vector. And so here, this is just specifying using 2 different model paths that have already been read into R. And so this is specifying where the estimation model is located, where the stock synthesis model is located. There's also an option to include the name for this estimation model. And so this will rename your model if it's specified in this directory vector. And we also have a few built-in models into the tool. So one that we've been using a lot for testing is the COD model. And so it's just called COD. If you just type the name in there and don't include anything in this directory vector, so just leave it as null, then SSMSE will automatically find that model and use it. So the next management strategy group of options is custom. So how this works is the user can create a function. So for example, here, let's say we've created this function in a file called customfunds.r. And so our function name is constant catch ms. Here we have some inputs. The first one is omdat. So this is required. This is the data file, stock synthesis data file resulting from sampling from the operating model. The next input is the number of years between assessments, and it's also possible to have other inputs to this function. So here are 2 here. So the user can write whatever R code they would like within this function. What's important is they output an object that includes catch. And so this is a list object, and what's important to include is either a value for catch, which is catch in the units, or I should say catch by fleet in the units that the stock synthesis operating model is expecting, or you can specify catch as a harvest rate instead, since those things are different. So one of those is necessary to specify in this case. So after the function is specified, the function can then be run in a call to run SSMSE like we've seen before. And this time in this MS-vec input, we would input the name of the function instead. So in this case, this is again a two scenarios that we're going to call, and both are using the constant catch MS, the function we wrote up here. Finally, the last input that's needed is a custom MS source. So this is just specifying the path to the file that contains the function or functions used in the management strategy. So we're hoping with this custom management strategy, this can really help folks define a wide breadth of management strategies that are applicable to them, because we know that it would be impossible for us to build management strategies into the tool directly that would satisfy everyone. So hopefully this will give flexibility. So now I'm going to walk through an example of the SSMSE tool. And so the question we'll be looking at is what happens if we don't account for natural mortality events in stock assessment. And so this is a pretty general question, and really this is just a toy example, but it can be expanded on, and it's applicable to a lot of real world situations. So for example, in the Gulf of Mexico, red tide, which is a harmful algal bloom, causes fish kills periodically. And this often needs to be accounted for in stock assessments, but it's really hard to know exactly what that value of mortality that red tide is causing. So this is this is a very simple example, but moving in the direction of answering questions that could be relevant to looking at things like red tide. So in this example, we'll be projecting forward 50 years. So this will be years 101 to 150 in our model, with a stock assessment occurring every 5 years. This will be using a cod-like species with one fishing fleet and one survey. And we have 3 operating model scenarios, which are 3 different natural mortality patterns. We also will be using 2 different management procedures, which gives us a total of 6 scenarios. And finally, we'll be running 50 iterations per scenario in order to capture some stochasticity within the simulations. Note for real world problems, you'd likely want to run more than 50. And for anyone who's interested, this GitHub link down at the bottom contains the code used to create this example. So looking first at the details of our 3 different natural mortality scenarios, we have 3 different patterns. So a natural mortality pulse that is high, one that's low, and then in a scenario with no natural mortality pulses. So on our x-axis here, we have our simulation years, which go from year 101 to year 150. On our y-axis, we have natural mortality, instantaneous natural mortality, I should say. And so first, if we look at this none scenario, we just have constant natural mortality at a value of 0.2. With the low pulse scenario, we have peaks of natural mortality up to 0.3 every 5 years. And then with the high pattern, we have a peak up to 0.4 every 5 years as well. So we also wanted to include process error in this example, and so we included recruitment deviations in the operating model. So here again, we have along our x-axis, we have the projection year, and along our y is just showing the recruitment deviation values. And so this is just showing for one iteration a random pattern of recruitment deviations. Note we specified or told SSMSE to run this by using that future OM list option that Nathan discussed, and we were able to also have it use the historical standard deviation. So the deviation of the recruitment, the standard deviation of the recruitment devs during years 0 to 100, and that was used to create these recruitment deviation patterns in the projection period. Furthermore, we wanted to include annual deviations in one of the length selectivity parameters for the fishery. So this plot here again shows our simulation years on the x-axis and the selectivity parameter value on the y. So the base value is shown in this black horizontal line, and then the blue points and line represent one selectivity pattern for one iteration once again. And so we had random selectivity varying annually. So what this parameter, what it influenced in the selectivity curve was the slope of the selectivity curve. And just to give you an idea of what this means in terms of the total selectivity pattern, I plotted the selectivity using the other parameters for the smallest value on this plot and the highest value. So we'll take a look at that. We have along our x-axis, we have our fish lengths, and then the plot on the left is the smallest value on that deviations plot, and then the largest parameter value. The color of fish shows how many fish were, or what proportion of fish rather, were selected or not. And so if you look, glance back and forth between the largest value and smallest value, you can see that there's some difference in what proportion of fish would be selected. So this does make at least a small difference, including this in our operating model. So now moving on to our management strategies, we use the EM option. So we ran a stock synthesis estimation model as the stock assessment. Our estimation model assumed that natural mortality was fixed at 0.2 in all scenarios. So it doesn't account for our pulse scenarios where natural mortality went above 0.2 in our operating model. The catches were set at a value expected to achieve a target to harvest rate to correspond with SPR 30 or SPR 45. And so this was set up in the forecast module of stock synthesis. And then catches were projected using this forecast module between assessments. So in order to understand the results of our simulation, we need to specify performance metrics. And so the Ponta et al. 2016 paper with recommended best practices for MSE recommends using at a minimum metrics for catch, variability of catch, and population size. So that's, we defined some metrics similar to that here. So we used output from the SSMSE summary all function to then calculate average annual catch variability as quantified by the coefficient of variation, and the average annual spawning stock biomass. We summarized all these values over the last 25 years in order to get long-term averages. So we ran our simulations using SSMSE. And then after the simulations were done, we used the SSMSE summary function and created our performance metric plots. So here is what we found. So starting the top left-hand corner, we'll look at the long-term average catch. So I'll walk through the plots first. So on our x-axis, we have our OM, our three scenarios with respect to the M pulses, so no pulses, the low pulse scenario, or high pulse. We also had two different management strategies, which are shown in the two different color violin plots. On our y-axis, we have the long-term average catch in billion metric tons. And then finally, on our violins, there's a horizontal line, and that represents the median value. So if we look at this first violin plot, we can see that there's little difference amongst the three OM scenarios looking across the same management strategy. However, we see long-term catch being slightly higher in terms of the median with the SPR 30, but also we see those distributions are a little more spread out. Looking now to the long-term catch variability, you can see, looking from as the natural mortality pulse magnitude increases, that catch variability decreases slightly perhaps, but the biggest difference we see is that catch variability is generally higher for SPR 30 management strategy versus the one to achieve SPR 45. And finally, the long-term average spawning stock biomass. For this one, we see that spawning stock biomass decreases slightly as the OM natural mortality pulses increase. But once again, we see the biggest difference being between the two different management strategies. So we see the simulations trying to achieve SPR 30 being right around the SSMSE value, whereas the SPR 45 scenario is a little higher. So what this means for us is, looking back at our question, what happens if we don't account for natural mortality events in stock assessments? We saw that we have similar catch across OM-M pulse scenarios. We see slightly higher coefficient of variation with higher pulses. We saw a small drop in spawning stock biomass with higher pulses, but we see overall the main differences are due to the management strategy used. For this particular example, we see little effect on the performance metrics by not accounting for the natural mortality pulses, which is good news. Of course, this is a very specific example and shouldn't be generalized. So just to go back to the SSMSE tool itself, what scenario should you, or when should you consider using the SSMSE tool? So it's a great tool if you want to run simulations where stock synthesis is the operating model. It also makes sense to use it if feedback to the operating model from the estimation method or management strategy is desired. If the goal really is just to use a stock synthesis operating model and a stock synthesis estimation model without feedback, then SS3Sim would probably be the better choice of tool. As long as the management strategy can be written, so it can take in a stock synthesis data file as input and output catch by fleet, then SSMSE will work for that purpose. So in all these scenarios, SSMSE is an appropriate tool to use. We also wanted to highlight that SSMSE depends on other tools. So of course it depends on stock synthesis. It also depends on the R package R4SS, which is a collection of functions, of R functions used to process stock synthesis input and output. And it also borrows from SS3Sim. So the advantage of depending on these tools is that we were actually able to add to them while we were developing SSMSE. So for example, in R4SS, we were able to expand the capabilities of the reading and writing of stock synthesis files into R. And so now anyone using R4SS also has enhanced capabilities to use those functions as well. So there are a few potential upcoming applications of the SSMSE tool that we're aware of. So one is looking at management procedure performance under climate change scenarios for Pacific sardine. There's also a project to look at stocks affected by red tide in the Gulf of Mexico. And finally, evaluating performance of data limited assessment methods for blue shark. So just to reiterate the key features of SSMSE, it has the ability to turn stock synthesis models into an operating model to use in management strategy evaluation. You can specify the data sampling scheme to use. There's also the ability to change operating model parameters. annually in the projection period of the MSE. There's options to use either a stock synthesis estimation model or to create your own management procedure using an R function, and SSMSE can summarize simulation output. So some take homes that we hope you remember is that SSMSE is an R package for conducting MSEs using stock synthesis operating models. And we hope that using this tool can, instead of writing entirely custom code, can reduce bugs, save time, and increase the reproducibility of management strategies using stock synthesis. SSMSE will be maintained by the stock synthesis development team, so we hope over time it will become even better. And just once again, I wanted to refer to our resources, including the README and the user manual. We also have, users can also ask questions on our GitHub. So we are using the GitHub discussions feature, so people are welcome to ask questions there. And so I'll just leave you with our GitHub repository link once again, and we can also be contacted via email, either through the stock synthesis email or through our direct NOAA emails. Thank you all for listening, and I think we're ready to take questions.
Great. Thank you so much, Kathryn, and also Nathan, who's rejoining us for the questions and answer session here. Audience, we have about 9 minutes to answer your questions, so please type them in the questions chat box, and I will read them to our speakers. And before I do that, I just want to remind people that a number of wonderful links were in the slideshow. So the speakers have provided their slides as a handout. So take a look at the handouts drop-down menu and download that PDF for your own use. Okay, so here's the first question. This is for both Kathryn and Nathan. It asks, wondering if on the OM side, if MCMC generated data sets could be used by the MS.
So that's something that we've thought about. I'm not sure if Nathan, I'm not sure if it's clear to you whether they're talking about the OM or the EM side, but we know that a lot of people will use MCMC in their operating models in order to capture variability.
Sorry, I don't mean to interfere. It's the OM side.
Yeah. So I think that was an option we talked about. That's not currently available, but it's something we could add in easily later.
Great. Another question asks, what's the best way to get started with SSMSE? Is there an R vignette?
There's a README on the GitHub, that link that was in the previous slide. If you just go to the main GitHub page, there's a full walkthrough in the README of a simple example that gets you going with all the inputs, and you can test along, and you can run it and compare yourself to what's in the README to make sure you're doing everything correctly and can understand all the errors it will spit out and the steps. So you should be able to replicate that. Would be your best way to get started.
Someone just said that the README works great, that they ran it during the talk. So kudos. All right, next question asks, does SSMSE allow for implementation error? For example, catch differing from the ABC in some systematic and a random way?
Yeah, so I mentioned that in those parameter variables you can put into the future. Yes, that one of those is implementation error. And so you can specify what you want your mean to be, what your standard deviation is, and it can draw a random distribution around that. So you can set up the specifications, or again, you can also put in custom values. So if you had specific implementation errors you wanted to test through some complex model, you could implement that as well. But yes, it does allow that.
Thank you. I'm going to wait another couple of seconds here for another question. And while I do that, I just want to remind the audience that if you know of people who might be interested in this topic, I encourage you to share the recording of the webinar with colleagues. I'm going to upload the webinar to the NOAA Central Library YouTube channel in a couple of hours after we end the presentation. And again, I have put the link to the YouTube channel in the chat box. So let's wait another couple of seconds to see if we have any more live questions from the audience. Meanwhile, before we get close to the ending, did you have any last comments, Kathryn or Nathan? Nope.
Just a comment that, oh, sorry. Go ahead, Nathan.
There you go.
I was just going to say we're happy to help if folks are trying to use the tool and they run into issues. We're more than happy to help, so please don't hesitate to reach out.
Yeah, that was exactly what I was going to say. Is we hope that everyone gets a chance to use it, and yeah, just reach out to us because it's takes a little bit sometimes to get started, and we're here to help and correct bugs as they come along. So the more people we get using it, the cleaner it gets, the faster.
A question just came in. It's actually a compliment as well. Nice work and nice presentation. In your episodic M example, did you examine the effect of different frequencies?
No, I didn't. That example was really put together to demonstrate the SSMSE package, so I didn't consider a lot of other options. However, I think, Nathan, you'll be doing some more work on natural mortality using the tool.
Yeah, so that's the project that we mentioned vaguely, briefly, Kathryn did, that we're going to be using SSMSE to try to look at the potential ways to incorporate red tide mortality into forecasts and OFL estimates. So that's the simulation I'm going to be working on with Scalus aggregates in the Southeast Center over the next couple of years. So we're going to be looking into that. So there'll be a lot more detail there on how you can incorporate in your assessments and also into your catch quotas.
Great. Well, I'm going to end this presentation with one last compliment from the crowd. It says, thank you, Kathryn and Nathan, for a great presentation. You're both excellent science communicators, and I have to agree with that. So again, thank you for the presentation, and Kristen, of course, for organizing the National Stock Assessment Science Series. I'd like to say thank you for joining us and to say that NOAA Central Library is very proud to present the work of the NOAA community and its partners. And we hope you'll join us again for another National Stock Assessment Science Seminar. It's hosted every first Thursday of the month at 3 p.m. Eastern Standard Time. So enjoy the rest of your day and have good luck. Bye-bye.
Thanks for having us. Bye.